Great.
For me? Good. So now when thinking of correlation, you quantify only a linear relation, and that's also important. We remember from class number 3, I believe, 2 or 3, when we talked about displays of graphics, we talked about linear and nonlinear relationships. This correlation, this is a linear relationship only. And this is important to keep in mind because nonlinear relationships is a much more complex approach, and that's far beyond this class. So we're quantifying it using the calculation of R, which is the correlation coefficient. So basically, we have a numerator, which is the sum of the products between deviations, not squared this time because we want to preserve the sign, because the sign gives you the direction. It gives you the direction whether it's a positive or a negative correlation. The difference between the positive and the negative correlation is when the x value, the independent variable, gets larger, the dependent variable also gets larger when it's positive, or gets smaller when it's inverse or negative. So this sum of products of the deviations divided by the square root of the sum of squares of both of x and y gives you a mark of the variability and allows you to essentially quantify the strength of the association. Yes.
So the top equation, so the sigma is the sum.
Sigma sum.
And then the x, that's the deviation from the mean. So y is it x, and it's like y is it x and y.
Because you have deviations on the x mean, so that's the vertical one. Right? So you basically have independent variable. There you have one mean. You follow all of that up, and then you see the deviations along this vertical line. And then you have a y, and they come together at one point, and that's the basically where this comes together then. Right? So that's the center point of your association. And this is when you think of the regression, this is where that line, that regression function goes through. That function point.
So what's the denominator? What's sum of squares?
The denominator is the sum of squares. The sum of squares is the deviation squared and summed. So this is basically on the pathway to variability. So you're creating a relationship between the sum of the product of the unsquared deviations, non-squared, divided by the square root of the actual squared deviation. So that's it's basically a direction. The direction of this correlation or association divided by the variability, and that gives you the strength. You remember the strength of the association, because that will be the main driver. That will be the main driver of your correlation coefficient. Just like we have with the standard error of the mean, for example, we have the standard deviation divided by the square root of the sample size. And the sample size, if the sample size gets larger, automatically the standard error of the mean gets smaller. And then in the calculation of a set score, the t-score gets larger with a smaller standard error of the mean with a higher sample size. Same principle applies here. Good. So that was the equation, and just make sure that you understand the components of this equation. And remember the examples we calculated. Always start with scatter plot. Yes, calculate these. We have the formula in the Excel spreadsheet. It has a standardization procedure. It is pretty much nothing else but standardization. So you're standardizing that sum of squares product. You basically, it's not a variance, but it kind of goes in a standardization direction. It basically standardizes it to basically get the strength quantified. Also keep in mind what a partial correlation is, and it's important to know what a Venn diagram is. That's actually quite an elegant way to depict data, because you will have different variables. And if you want to assemble a set of variables that you want to analyze in more detail, a Venn diagram is a very interesting way to kind of calculate where do these three variables come together, and then analyze it with correlation and regression tools. Also, don't forget the psychometrics. Know what the reliability and the validity is. Understand the test and retest reliability. So that's basically, so every time you repeat a test, it should yield the same result. That's quite important because otherwise the test would be rubbish. And also, if you want to use a test like that in clinical practice, changes in the test may actually mislead you to think it's due to changes in clinical characteristics of the patients. A way to quantify reliability in having one test at hand of a population, of a sample population, is a split half reliability, where basically you correlate the odd numbers with the even numbered items. That just means essentially you have a test of 100 questions. All 100 questions mean to quantify one outcome. And if you take 50% of these, just randomly picked, or just the even numbers, they should in the same fashion point towards the same outcome, and they should correlate highly. If they don't, you have a problem in your test items. You also have the Cronbach alpha or coefficient alpha, which is essentially the same aspect. So you take split half correlations, and on a population, you basically want to correlate these means for your split half correlations. And they actually mean to come to a correlation coefficient of at least 0.7. Otherwise, the test is not internally consistent, which is the technical term for it. And validity is that that test essentially should be measuring what it's meant to measure. And to establish this is, again, establishing causality in a way, because you mean to correlate it with clinical characteristics. If you have a quality of life outcome and a certain fraction of your population, of your sample, says their perception of their general health, which is done with a quality of life questionnaire, which is quantified, self-reported perception of your own health. If half of these patients say they're not feeling well, and the other half is actually doing pretty well, this should correlate with clinical characteristics. So if they're sicker, they will give self-reported lower quality of life or a lower perception of their own health. So that's basically how you can establish this causality and establish this correlation and validity of your test. Yep. Personality quizzes to be taken with caution, likely not very useful and definitely not validated. Validation is interesting because you need to validate and I think I said that when we talked about it the first time, you need to validate each and every single item of your test in different population, in different regions, languages, cultures, you name it. You really need to make sure that you capture with your test what you want to capture. So you will see if you go through PubMed, for example, and you look for validation tests, validation of surveys, you will find a plethora of a million different papers trying to validate surveys in different populations. So before you, for example, if you run an international study and quality of life, for example, is one of your outcomes, you need to make sure that one of your contributing partners who is in a different country actually has a validated study to validate this particular survey in their population. So that's very important that you communicate. Good. Any questions about correlation? I think it's considerably simple, right? It's not complicated in a way. So now we're going to talk quickly about regression, and we're going to pick then off where we stopped last time with multivariable regression, because today we're going to do multivariable regression in R. So regression is basically the continuation of correlation. And now we're not only quantifying the association, we're also utilizing this association to quantify predicted values. That means that we're building a function that allows us to mathematically derive a predicted value of what we think the dependent variable would look like if the independent variable takes on a particular value. Is used, and then we will talk about examples, is used in your daily life. Your phone does 1 million multivariable regression models probably per minute or second. So every app on your phone will do exactly these kind of methods. mainly logistic regression, which is a more advanced method, but it's in our daily life. So basically what you do, you estimate a standardized y, the y hat, predicted value of your dependent variable. It's standardized, so it's a set score. And you derive that by basically standardizing your individual x, and you're multiplying it with your r. That basically gives you an idea about the direction and the strength of this association. And thereby you can estimate your predicted y hats. And that allows you to estimate particular value and derive your function as a slope and as an intercept. Good. Also the explanation of the regression to the mean, because you're basically using standardization, which standardizes to the mean of x and the mean of y. So we have done the calculations. I don't want to go through the calculations much, but I highly flag this as something very, very central. So the y hat, that's the predicted value. And the predicted value is predicted as a plus b multiplied by x, where a is the intercept. And this is by definition the y value, the value of the dependent variable, where x equals 0. And that will be the same for all methods. B multiplied by x, that's the slope. X can take on any value that you have in your data set. Can be also not in your data set, because you can use this also to extrapolate it beyond the data you have at hand. And it basically, by definition, the slope is quantified as the increase in the dependent variable with 1 unit increase of the independent variable. So irrespective what your independent variable is, it's 1 unit increase. Whether it has a unit, whatever the unit is, sometimes you even deal with parameters that do not have a unit. In my world, we have a couple of ratios that we quantify for our patients. Then you take 1 unit increase. Even if your data does not have increments greater than 1, so it only deals with decimals, even then this slope will automatically be 1 unit increase. If you want to get it to a decimal increase, what you're going to do? When you divide that by 10, then you get it to 0.1. Good. Regression with set scores. We talked about this. We've seen that formula earlier. Keep in mind how to standardize, but you know how to standardize, right? It's basically the individual x minus the mean divided by the standard deviation. Again, standard deviation, not the standard error. That's important to keep in mind. Good. Okay, equation for a line. We have done that. We have calculated this line of best fit. Just keep in mind, if you want to do an estimate, you only need 2 data points. You just need 0 and 1, and maybe 1 and 2 to confirm. But you just need these 3 data points, and you can establish your regression function. So prediction. Well, think about, let's go back to our spreadsheet. When we did the spreadsheet, you remember this calculation. So we went all the way from calculating all of this. We calculated the residual error, we calculated our R, and here is basically what the prediction is. And this here, when you look just at these components here, so those were stressful life events. So we have regression scores from stressful life events. So our independent variable is stressful life events. We have 3, 2, 1, 0. You don't even need 3, but it comes back to that. You basically have a standardized set X, which is you have the mean of X. You standardize, you get an individual set score, which logically, so the mean here was 1.9. So everything smaller than 1.9 will be negative. Everything greater will be positive, just like we always standardized, right? Multiplying this with the correlation coefficient gets you to a standardized y hat. And with the standardized y hat, you just need the actual mean of y, which was 15.7. Basically gets you to an actual y hat. And the only thing you need now to to determine your intercept and your slope is to take the value at 0. That's your intercept because x equals 0 there. And you need the difference between x equals 1 and x equals 0. That's your slope. So it's that simple. Alternatively, you can also do it differently. So you can, hypothetically, you can also calculate it. So there's this formula that will allow you to basically calculate the slope. If you only have data points, let's say you have 2 data points and you want to calculate the slope. You can do this by y2 minus y1 divided by x2 minus x1. But you likely have learned that in high school. Because this is basically the calculation of a linear function. You can calculate like this. So you have 2 points. This is your y coordinate, your second point. This is your y coordinate of the first point. You're subtracting these 2 and you divide it by x2 minus x1 gets you the slope, gets you the increase as a function of increases in x. And if, yes. So if you, for example, if you would do this now with, let's say y2 is now 12 minus 9 divided by 1 minus 0 comes down to essentially 12 minus 9.5 divided by 1 minus 0. And that's exactly what we have found here, but just calculating the difference between this and this. So this difference is essentially your estimation. So this is just the mathematical derivation of this. Yeah. So what's important to keep in mind with your predicted values, a prediction is only as good as it actually performs. And unfortunately, predictions are not always as good. And you have here 2 different depictions of 2 different predictions. So I guess, I hope it's obvious that this prediction is substantially better than this one. Why? Because there are more points further away. So overall, you need to kind of quantify that, right? And this is what we did by quantifying the so-called residuals. And the residuals are basically the distance of the individual point from the point it would have been were it predicted by the function. So it's basically it's the distance between the point and the line. That's what we quantified. And now I'm going back to this spreadsheet because we did quantify exactly that. We have quantified the sum of squares of y. And the sum of squares of y is basically nothing else but just like we always calculated our squared deviations from the mean summed up. That gives us an estimate of the overall variability. So that's the deviation, the sum of squared deviations of each individual point from a flat line, which is basically representing the mean of y. So now, this being said, that's our total variability. That's all the variability in our data set. Now, next we want to calculate our residual error. And we did that by calculating a y hat. If you remember the formula of y hat, this is basically our regression function. So we're taking now b2, that was our x, multiplied by the slope plus the intercept. Gets us a predicted value. So we're using this function to estimate, predict our y as y hat. And now the only thing you need to do, and this is this column here, this is calculating the difference of the predicted y minus the actual observed y. That gets you this residual, this difference of the individual point from the line. And this quantified, if you sum this up, that's 0. Why is it 0? Because it's fitted through. And by standardization, by using this method, we're using a method that is called the least square method. The least square method is basically we're minimizing the squared deviations. So we're fitting this through in a way that the squared deviations between the individual observation and the predicted observations is minimal. Least square method. Again, yeah, a term to keep in mind because there are different ways to approach this. One would be the maximum likelihood estimation, but that's a different class. So now taking this residual, squaring it gets you a squared residual error. Summing this up gets you a sum of squares of the residual error. And this is now the leftover error. This is literally after employing your function, what's left of your error. And now you can quantify what proportion of your error is being explained by your function. And logically, this is now the total variability minus your residual error. And this difference is the benefit you get from filling a line through that is not flat, but is basically tilted according to a least square estimation. Make sense? Any questions? I hope conceptually it makes sense and you're following along because the concept is so super important. The calculations like you can look at.
Can you say it again?
Sure. We're quantifying the total variability by calculating a difference of each individual observation from the mean. The mean being a flat line that represents the mean of y. You're getting the sum of squares, just as we always did with when we calculate standard deviation of variance. So now you predict the y hat, you predict your individual values according to that function that is not a flat line anymore, but has a certain slope with a certain intercept and fits minimizing the difference between the individual point and that function to the furthest, to the maximum. So it minimizes these differences. You're filling that through and you use this to predict the individual point for each of your 10 patients. Then you're summing up the differences observed between the predicted value and your actual observation. By that, you basically get a residual error squared if you square it up, and then you get a leftover error. And this is the leftover error employing that function, employing that model. So this is lower than the total variability because now we're tilting it and we're having a certain intercept. So there's a certain function in there that kind of captures more of that error. And the difference between these two, that is what your function has explained. That's the sum of squares of the regression per se. So this is the explanatory power of your function. And if you take this this explained error and you calculate it as a fraction of your total variability, you get to the proportional reduction of error, to the coefficient of determination, R squared. And that is super important to keep in mind because that will be on the quiz on the final 100%. So the understanding of this is very essential because it's a reflection of the explanatory capabilities of your function. And if you build, and that's another fact. So now we're getting into multivariable regression because not only would the regression score be explained by a number of stressful life events, but if you include an additional variable, you would increase the predictive qualities of your function. So you get more accurate in your prediction. You're not only predicting it based on one variable, because that's also it's quite unreasonable that this would really explain how depressed the person is. So you get additional information in there, so your prediction will get better. So your sum of square regression increases, and thereby the R square will increase as well, because now you have more error explained. But we'll talk about this in a second. Okay. Any other questions on that? Does that explain your question? Yeah. So standard error of the estimate, you will always have errors. You quantify the proportional reduction in error. That's your R squared. And so here, this formula exactly is that. So we have this total error from the mean. This is the sum of squares error. So this is the leftover error. The difference between these two is the explained error. And we're dividing it by the sum of squares total, which is the total variability again. Gets us an R squared. If you want to visualize it, I think that's a very nice way to visualize it. So you have a mean of y, which is 15.7. You have these individual differences between the mean and your individual data point. Gets you exactly these differences. That is your sum of square total. If you fit the line through, your residuals change, they get smaller. And you minimize them, and you get the line of best fit. And so this is what's being explained, the difference between the sum of squares here and the sum of squares before. That is your explained error. Good. Regression to the mean we talked about, because it goes through the mean of y, mean of x, it will automatically regress to the mean. Your predictions, multiple regression. And now it's getting really interesting, because with multiple regression, you have an addition, you have a technique that you can include more of these predictor variables in your model. So now when thinking about depression, stressful life events, yes, there may be an association with depression. And people that have more stressful life events, yes, they're more likely to be depressed. Okay, that makes sense. Causal, right? Could be a causal relationship. But you want to see whether this in addition is being affected by sleep disturbance. If somebody can't sleep, he or she may be depressed as well. So that may be an independent association. But it also may jointly go into a model predicting the depression. And the way to do that is to add both parameters of both variables into a multiple regression model. And this here is model outputs that is quite standard, and that you will see from whatever statistical software will somewhat look the same. This is from SPSS. So I don't know, those of you that go into psychology, you may need to utilize SPSS. It's very popular in the psychology world. I highly recommend to use R rather than SPSS. I spent my days with trying to understand SPSS and I still fail to understand it. But it's basically you have a standard output for such a multiple regression. So essentially, you see the actually included variables. You get the intercept, which is constant. You get an estimate, which is a slope estimate. It's nothing else but a slope estimate. Essentially for life events and sleep problems. So in unstandardized coefficients, you get exactly what that means. It's an unstandardized coefficient. So if we have a standardized y hat, this would be standardized coefficients. Unstandardized coefficients is basically once you have restored the actual magnitude of the value, and you get here a so-called B, which is the slope, and you get an actual standard error. You also get in the same context, you get a t-score, because it follows a t-distribution. Back to what we discussed before, is like this is basically where there is kind of the overlap with t-distribution starts to happen. So we're basically dealing with t-distributions. And so you will basically be able to quantify significance, which is basically a type 1 error that is less than your acceptable alpha of 5% and 99%. Will be determined based on that t-score. And that t-score is basically the variability of your prediction. So that's determined by the residuals around your estimate. Good. If you have a formula like that, and this is now where it's getting interesting. So if you have, in addition to that, example of stressful life events, let's move this just over here. Let's just grab this part and let's bring this in a second spreadsheet. So now we have these values here. If we would now if we're getting the sleep disturbance score over there, we can now essentially do exactly that calculation. So now this is our sleep disturbance score. And we will deal with that in a second in R, because in R it's just much easier to do multiple regression. I'm not even sure Excel offers that, but it's possible. So now we have the sleep disturbance score in here. So if we were to estimate now the actual value, and this is where multiple regression actually is quite elegant, because you can do exactly the same exercise as you did before with the y-hat prediction. Because now the formula that you're looking at, and this is literally something to be flagged for the quizzes, because you will need to predict things. So you have now unstandardized coefficients. Again, we have an intercept, which is minus 4.117. Then we have plus 1.194 multiplied by our life events, plus 2.089 multiplied by our sleep problems. So this is how you will approach predicting, again, your dependent variable, utilizing the printout or output from a multiple regression. And it's, if you want to bring this now into practice, you can now calculate your y-hat. And your y-hat is here, minus 4.117 plus 1.194 multiplied by the actual number of stressful life events, plus 2.089 multiplied by your sleep problems. And that's your predicted depression score. And that's how simple that is, essentially, to calculate and predict using multiple regression. If you were to oops, no, it's fine. So if you want to know now the deviation that we calculated before, so we do now the residuals, is now this estimate minus our actual observed back depression score. We get now a residual which is substantially lower than what we've seen before. And if we are squaring this, so that's the squared residuals, that is basically now our sum of squares. That's the sum of squares. Oops, error. So that's the residual error. And please know how to do that, because that's very essential, very important. So you have now a residual error of 79 from a previous 526. So you have substantially reduced that error that is left. So if you take now, I didn't bring this over. So we have now here a total sum of squares of 788.1. So if we have to calculate now 788.1, so that's sum of square total. It's 788.1. So now the sum of squares regression is now this minus this. And if you want to calculate now R squared, this is basically the sum of squared regression divided by the sum of square total. And we're getting now to an R squared of 0.89. That means that 89% of your variability is explained by this model with both parameters involved, with both variables included. So now I know this is now a lot to take in, But think about the brilliance of this, because before you had the stress for life events, you only explained 33% of your variability. Now you have 1 second parameter in there, which is the sleep problems. Now you all of a sudden, you're explaining 89% or 90% of your variability. So that's where you're going in a direction to really solidly corroborate a potential causal relationship. Corroborate, not establish, not confirm, but you're kind of pointing in that direction. There could be something in there which is worthwhile studying in more detail. Okay, so this is multivariable regression and how you utilize it in your daily life. And we will now, just one more slide. Any questions to multivariable regression? I know it's quite a bit to take in. It's like, I know, but it's please rewatch the recording, because that's what we just did is what is being done on a daily basis in your apps, in your day-to-day life. And this is why this slide is a good final conclusion slide, because it is very central that we understand this, because it's really used for various aspects. It's used on apps and websites. They predict everything that you are interested in. It's forecasting of your shopping behavior. You open Amazon, but basically Amazon suggests to you, you may want to buy this. Okay, so I know I use brand name, I shouldn't do that. But basically, wherever you log in, it will suggest to you that you're interested in something. This is all done with multivariable regression, notably logistic regression and less likely multivariable regression, but that's a big one. Anticipatory shipping. If any online reseller guarantees a one-day delivery, this is done because they're filling their warehouses based on shopping behavior of whole cities. Shopping, shipping, yes. Shopping, same thing, right? It's like you go anywhere in a supermarket that basically gives you tailored discounts of what you may be inclined to buy. And this is where multivariable regression is just very central. So these models are built in a very sophisticated manner. We have seen now a model with 2 variables included. In predictive analytics, you have up to 100, 150 parameters in there that are being collected from you on a daily basis. Good. That was this. So now we have 20 more minutes for our practice lab. Now, I like that enthusiasm.
You're so fun.
Okay, great. I like the enthusiasm. Good. No, don't be scared. Why would you be scared? Yes, we're opening up.
Practice that 4 solutions. Practice that 4 solutions.
Yes, 5, not 4. It's called initial solution or something like that.
Initial code.
Yeah, initial code. So you open RStudio, and you click on open. You click on open and you go in your, hey.
5 in court.
I need a camera. Okay. So RStudio, you download Practice Lab 5, initialcodes.r. You open this file and you see this. So this is a code of 33 lines. Okay, first we're gonna do, as always, we have on line 2, we're removing everything from our environment because we don't need it anymore. Control and control. Just line 2. Okay, good. Control enter now in line 2, and now line 3 will create a data set. That is the data set of our students. That's our 10 students. This is consistent with what we've done. Yeah, I just clicked on it. So this is DFM22, should be 21 actually, but detailed. Okay, so we have on line 7, you basically, you kind of, you look at the data set with LS, you get a list of variables in your data set. Contains absences, grade, and student ID. You only interested in absences with DFM22 $ absences, you address only that one variable. And you only get all the entries for absences. Good.
Wait, which part? You just did control on 28?
Yeah.
Yeah. So now you can also, you can pack this in a separate object. You can make absences a separate vector by basically just running line 9 will create here a vector of 10 entries. And this is where you extract part of your object and you make it a separate sub-object. You can do the same with grades. Yeah. Okay, now first, we want to understand, do these two variables correlate? There's the core function, COR. The way it's shown, I pack everything into a separate object, and you do this with this sign, which is a smaller sign hyphen. That basically will pack whatever you do afterwards, whatever you tell it afterwards, it will pack it into this object. And if you do this with line 12, you get now an object cof1, and cof1 basically contains a numeric value for this correlation coefficient, which is minus 0.85, which is the same as we quantified. Good. So this is how simple that is in R. Now you can also, if you just click in the console and you write cof1, it gives you exactly that value. So you can call it anytime. It's safe for eternity.
Enter.
cof1.
What did you just say?
So you save
In here?
the result of this function in your object. So now you have assigned to this object, you have this one value.
The bottom section.
Yeah. And now we're doing something which we haven't done in the correlation example. We build our first model fit. We're fitting now grade as a function of absences. The way this is done is with the function LM. LM stands for linear model. LM, and then you have here your dependent variable, followed by the mathematical tilde, and the independent variable of absence. So the tilde is on the left top. It's basically right next to the 1, and you press Shift. That gives you a tilde. No, next to 1. Next to 1. It's Shift. So there's a button. So the button next to 1 on your keypad. It's called Shift, and that it is called a tilde.
I put it between the F and the I. Between F and what?
No. You don't need to put it. Just know where it is. The tilde is here. It's here, but that's how you build, and that's how you find this symbol. Good. If you, select now only or click anywhere in line 13. Don't select anything. Just click on line 13 and run line 13. Now you get something new. You get here fit 1.
Yeah.
And fit 1 is your model. And fit 1 can be called and characterized by summary fit 1.
Did you control like that?
Control Enter on summary 1, on summary of fit 1. That gives you this. And this is a little bit more complex, but let's walk through it slowly. What you have here, core, gives you actually what you call. That's the formula. That's what you ran. The residuals. That's the distance between your individual data point and your predicted data point. So it gives you for your 10 entries which is, by the way, here on your degrees of freedom, because your degrees of freedom is 8. It's 10 minus 2. Keep that in mind for the quiz too.
Why is it
and the
minus
final,
2 and not minus 1?
because you have 2 variables. You have 2 sum of squares. That's a tricky question with the paired sample t-test and the correlation. The degrees of freedom is determined by the number of individuals, not by the number of essentially entries in the variables. That's important as a distinction between paired sample t-test and independent sample t-test. You have 2 samples in independent sample t-test. Your degrees of freedom are separate for each of the samples. But here the degrees of freedom is determined by your sample size. Your sample size here is 10 students. Minus 2 for 2 variables, because it's 2 sum of squares. Good. Okay, the residuals. So these residuals are essentially a depiction of the actual differences between the individual observation and predicted value. This is normally distributed around the mean of 0. So your median is here shifted to the negative. So your median is actually less than your mean. What does that mean?
It's not normally distributed enough.
Ah, perfect. Very good. Exactly. As soon as mean and median are not equal, you kind of have some form of skewness, which may not be as bad, but the median is rock stable. It doesn't move. It doesn't move with outliers. But if you have a mean needs to arithmetically move right away. As soon as you have one outlier, the mean moves.
That's why the mean, yeah.
Exactly. Outliers.
Yeah, it gets very extreme,
Exactly.
but outlier.
The median will change if you have a lot of outliers, or extreme. Depends on the estimate, but basically it will shift at one point. But the first one that changes is the mean. Know this for please. Okay. You have now a characterization of this normal distribution curve. You have a median. The mean is not stated, but we have here Q3 and Q1. What is Q3 and what is Q1?
Oh, the quartile range.
Quartile range. So the interquartile range is from Q1 to Q3, which is here somewhere in the ballpark of 12. That's the IQR. Then you have min and max, and yeah. So that's the characterization of your residuals. Then you have the coefficients, and we know what that is. We know the estimate. We know the intercept is 94. We know the absences is minus 5.4. We have a standard error, which is the accuracy of the prediction. We have corresponding t values and the derived p values. Then we have a lot of asterisks here, which basically indicate the level of significance. So it gives you different levels of significance. Then you have a residual standard error. That's basic quantification of the residual standard error of your overall estimate. So that's the overall model. How accurate is it? And then you have an R squared. You have a multiple R squared. That is basically exactly that R squared we calculated. Now for ours, just for life events. And you have something that is called an adjusted R squared. An adjusted R squared is, we talked about if you include additional variables, you will explain more variability and more error. That means your R squared needs to increase with each variable. You can hypothetically include up to 1,000 variables or 100 variables or how much you have, but the problem is you're overfitting your model. So I'm not going to go into arithmetics of adjusted R squared, but the adjusted R squared is a different formula that is amended so that the estimate of your R squared is penalized for the number of variables included. That means it's going to be lower than your multiple R squared. That's important because usually you only report the adjusted R squared. And then, and here we're back to the ANOVA. That is a marker of between groups and within groups variability. So we have in F statistics, we have one variable at 8 degrees of freedom. And with the F statistics, we have now an estimate of our overall model. That's the p-value of our overall model. So we have a significant prediction. So that's the summary output from R. It's a little bit more complex than SPSS, but it's also much more insightful. If you click now on LS summary fit one, and those of you summary fit one, yep, this is all the information that you can get out from R. R has all this information stored in this model. So there's much more in there that you actually see here, and you can actually dig deeper by looking into this model. And we will do this later on. So you can, what you also can do, and this is like if you do plot fit one, you're actually getting here something very interesting. Plot fit one. You get here plot fit one. You get here very fancy graphs that basically show you so-called diagnostic plots. And don't think too much about it. It's far beyond the scope of this class. But it's interesting to see because this is an analysis of these residuals. This is an analysis of the residuals, and this is how you will. So you will basically, you see a diagnosis of your regression model, and with that you essentially can confirm your insights from your regression model. You get various. Yep. So this is a so-called QQ plot, where basically you see your standardized residuals as a function of the theoretical quantiles that you have quantified. You have various other depiction ways. You have standardized residuals as a function of fitted values. So you actually see where the inaccuracies of your predictions are. And you also test for homoscedasticity, that the variability does change across the magnitude of all your values. And you also get an idea here what values. You just press enter. So it says hit return to see next plot. That basically gets you to the next plot. And now I'm just trying to find my plot again.
Yeah. No, but then you have to go again. Where should you?
Yeah. So this basically tells you at what level of differences you actually have most leverage. And you see here that this level you actually have from your residuals. You just present them, you get them. So these are diagnostic plots, which are far beyond the scope of this class, but I just thought it would be nice to look at them. Okay. So this all awaits for you in future statistics classes. Okay. So what else? Yeah. Then we also have here fit one. We did now, and now we do the next line. And this is important when you write a statistics paper or you write some research paper in any of your classes, and you want to utilize R. So this formula here with plot allows you to develop a scatter plot in R. You can, with appline, you fit a linear model through that. So that's a depiction of your line. And with text, you basically include a correlation coefficient in your model. So this is basically how you can create graphs in R, which I may be biased, but I think they're prettier than other graphs. At least I like them more than Excel graphs. And you can basically, do a lot of manipulation in these graphs that are beyond the scope of this class again. Okay, so now we don't have much time left, but we go, we go right away. We go on the next example. We only have 2 minutes left. So we go on line 19. 22. Yeah, now we get an additional data set, which is basically the data of individuals, stress for life events, back depression inventory score, and sleep disturbance score. The same analysis we just did in Excel. we have now, we do the same thing, we do coefficient 2. It's our 0.58 correlation coefficient. Fit 2a is the fit without sleep disturbance score. So that's the univariate analysis we did. 3.24 and 9.542. Sounds familiar, I hope. And then we have fit 2b.
Did you skip the 29?
No, you can always do 26 and 28. That's just the new plot. That's the same plot.
Okay, so then we're up to 29.
And then 29 is fit 2b. That's the multivariable model. And here you get the same model as we have from SPSS output. So 930 basically gets you the same model as you have from SPSS in the slides by Nolan and Heinzen. That's 29 and 30. Gives you the multivariable model.
Should we run 32 or no?
Yes, you can run 33. 32 and 33. And 33 gives you again these plots that we have looked at before. And all you need to do to complete practice lab 5 is to copy everything down in the console. Don't forget to press enter, enter, enter with these diagnostic plots.
Wait, how many?
4.
So what line? Till 34? Wait, can you go down to the last, the bottom and enter?
Yeah, you press enter 4 times again. Yeah, you just press through. Okay. Now all you need to do to finalize practice lab 5 is to open the text editor. You copy everything in the console. You copy everything in a text file. Yep. You save it as STAT1021F. 1021F with your family name and practice lab 5. And that's your practice lab 5. And it's a fun R code. It's a very useful R code. If you choose to do R, these codes, I think will be helpful for you moving forward. So that's all for today. Thank you.
I think I made a mistake over here. So then I just kept, I did. So like, what do I do?
You're just gonna go back. No, it's left.
Because I accidentally copied like this. So then I ran it again. Thank you. Thank you. So now I copy this and send it to you or this? Yeah.
Everything in the console. Left.
Thank you.
You're welcome.
Look right. I don't remember looking like this before.
That's right.
It looks right? Okay.
Yeah. Thank you.
Thank you. Bye-bye.
Thank you.
Thank you. That's the last practice lab. Well, you get a chi-square code from me, but that's the last method.
Thank you.
Thank you.
Yeah. Thank you. Come now. You're helping. And you're my go-to helper. Are you ready? Yeah.
Thank you. You're welcome.
Have a great day. Thank you.
Thank you. Bye-bye.
Yeah, you can take your car.
Thank you. Yeah.
Thank you. Bye-bye. You too.
Just want to let you know that to leave class like 10 minutes early.
Okay. Thank you. Hi. Shall we? Right. Welcome back. I'm glad to report back that obviously my quizzes are too easy. So, no. So please make sure to not underestimate the final, though. I just want to emphasize this. It's just it's more questions, it's more material, and make sure that you're on top of things. So again, final will be 35 questions, 70 minutes, and it's I looked back your request to do it on a different day or to reschedule it. It's like it will be hard to accommodate, and so who is really affected by this in a very adverse way? Because the only way to accommodate this would be for us as a class find an alternate day, and that's going to be a tough one. So I think we should remain on a go for 12:30 at noon. And is there anybody really terribly affected with booked flights or whatsoever for that Friday? Saturday night?
Yeah.
Okay. All right. So I cannot change this date. It's like I look back upon request by you guys, and I know this is not the most optimal time. I'm well aware. So the only thing I can offer is like that you get in touch. If somebody is adversely affected, get in touch with the dean's office. It's fine that you take it on the day of the F class. It's fine with me.
What day is that?
The 28th. But it will likely conflict with other finals because they have a very tightly planned through schedule.
What day is the 28th? Oh, like Thursday?
That's Wednesday.
Can I come late to take it or no? It seems like I have to be there at the time.
Noon. Yeah.
Oh, yeah. Is that 9 AM or 1 PM?
12 p.m.
I think
It's noon.
9.
Yeah, it must be 9. So they calculated it through. Otherwise, you need to loop back to the dean's office. So Professor Jill Katz is the responsible professor doing the scheduling, and I think this should all be accounted for. But loop back to her in case of questions. I accommodate if you have any requests. I'm working along. I just don't want to come in an additional day, as you can probably imagine. But yeah, yeah. So keep me involved in the discussions if you want a different day. Happy to work around your schedule too. Good. Okay. Monday we do the next quiz. We do ANOVA, chapter 12 and 13, not chapters 14, so it's only 12 and 13, and we're doing correlation and regression. I hope correlation and regression is not the most complicated topic, but it's a very essential and very important topic. And you will get today in Practice Lab 5 a little bit of a taste what wonderful things can be done with regression, because it's really, it's a very efficient tool to kind of test inferences and associations. Good. Let's log in here. What's happening here? Just a second, sorry.